So thank you everyone for coming. Didn't know how many people would be interested in this subject. We're really looking for people who are really interested in this, particularly from the modeling and simulation perspective for this meeting here, and appreciate everybody joining online. And we will talk a little bit here now. I'm going to give an introduction, then we're going to go into our speakers. This is our agenda for today. So I'm going to give some this opening remarks. We'll have a bit more from the operational perspective, Rex Alexander. We're very pleased to have Mike Price, Dr. Mike Price from the UK CAA, all the way here from the UK. I don't know if we're going to get anybody from the FAA.
I'm on there here, Mike, although I know I don't count.
Yeah, well, you count to me, but yeah, we're looking to have a speaker from the FAA Office of Airports. They have a lot of work that's going on right now in downwash and outwash for helicopters and looking towards advanced air mobility. But because of the current situation with the U.S. federal government, there's a general ban on travel and kind of a gag order as well. So we're probably not going to have a speaker then talking about all the work that they're doing. But we are going to be recording this, and so we'll be able to present it to them as information that they can incorporate in their future planning. Then we have Mickey Radetich from NASA Ames, and then three of the top modeling and simulation researchers in this area who will be speaking. So that'll take about we have a 2-hour session here. That'll take about an hour and 15 minutes or so. And then we'll have a discussion about what do we want to do with all this information. There's something useful that we can do as a Vertical Flight Society and the technical community. So this is nothing new, but there were some big headlines earlier in the year when when the FAA published a survey of some eVTOL, downwash, and outwash measurements. We've started a web page, VTOL.org/downwash is a landing page, and downwash-library is a library of about 50 or so reference documents that go back all the way to the 60s. This has always been a well-known critical area for high disk loading aircraft, VTOL aircraft, Harrier F-35B. This is a key challenge. When I was a young engineer working on the Joint Strike Fighter program and high disk loading rotorcraft as well, like the B-22. But it's now becoming more of an issue for civil helicopters as they have increased disk loading over the decades. It can cause serious damage, injuries, and even death, and it has. Generally, with a single main rotor, the perspective has always been it's kind of a uniform conical shape. We'll see some research today that indicates that's not correct. But if you have multiple thrusters coming down and hitting each other, they're going to have a stagnation line, then push out in the different directions, either fore and aft or multiple spikes where the stagnation lines come together. So this is really important for helicopters. That's really more of the focus on this at this point, but looking with an eye toward the future, advanced air mobility aircraft have their new configurations and have higher disk loading, and they're intended to operate at higher tempos and probably in closer proximity to passengers and others. So this is an area of concern, not just for helicopters, but also for future aircraft. So there's kind of 4 different things here. We're really only going to focus on one of them, this thing. But to give you more perspective, so generally helicopter pilots, at least civil helicopter pilots, aren't really trained to understand and manage downwash and outwash. And it's been recently coined DWOW for downwash and outwash. Maybe we can come up with a better term. There's also no accident reporting system. So injuries, damage, usually settle out of courts. There's no public record of incidences. There's no good databases of Rotorwash test data for hover approach and departure. And, based on the FAA's report that came out just before the end of the year, was basically the CFD models aren't adequate for today. So that's really the focus of this. But just, needs to be not our domain, but it means more training and procedures for helicopters and advanced air mobility operators. Cliff Johnson here from the FAA. The FAA is exploring incorporating this into the Aviation System Information Analysis and Sharing System, ASIAS. So there'll be more of a tracking system for when there is downwash and outwash incidences. The FAA is testing many, I don't know, dozens of different helicopters over the rest of this year. In our reference library, the Downwash library, there's lots of studies on and testing of helicopters, including Army for tandem rotors and some other configurations. So there is maybe data that the FAA can access for that. Maybe something, an outcome of this could be maybe it's an MOU or something, joint effort with FAA and NASA and the Army and industry. And then, what about models, right? So that's really the focus of this workshop. So, what can we do to help? So we want to have a good technical discussion today and come to a consensus on whether, we want to do anything about it. We're really here, they talk about forming, storming, norming, and performing. So we're here, we're in the forming stage. Do we need to form something? Is this something that we, the technical community, want to really grab onto and engage in? So if so, then, maybe it's forming a follow-on discussion group, working with stakeholders. I mentioned some of the government agencies. There's some different potential go-bys or analogs. There's a AAA hover prediction workshop with the Army and the High Performance Computing Center. There's HART, STAR. Actually, STAR is having a meeting right now. And then specifically, right, so I mentioned these web pages, this Downwash landing page, Downwash library. We have a hover community discussion group, right? So we could start one on Downwash and Outwash if you guys, we want to have a discussion on that, and then look at emulating other types of working groups that they've done in the past. So with that, that's my welcome and introduction. I'm going to introduce now Rex Alexander, unless anybody has any questions or statements before we continue.
Well, thank you very much for everybody being here today. We've been talking about downwash and outwash very eagerly over the last couple of years. I've been dealing with downwash and outwash my entire career as a helicopter pilot in one way, shape, or another. With that, one of the things we talked about is what is downwash and outwash. So here are a couple of short videos that really probably present downwash and outwash better than I can. Oops, if it'll play. So a good illustration of what downwash and outwash looks like for the entire approach path. This is an interesting video as the aircraft gets heavier because it puts on more water. You can see the waves on the edge start to get larger and larger. And this is just a helicopter pilot out to make new friends. All right, so some of the hazards we deal with in downwash and outwash. Having worked in EMS for 20 years, one of the briefings I give to all the medics is don't leave the door open. Had this actually happen to me. Tarpaulin tried to make its way through my rotor system. I luckily dodged it. Heliport in the middle, up in the right-hand corner, you see the white truck and the people walking by. The tailgate's down with a tonneau cover, downwash, $250,000 later and 9 stitches. And this is just fun to watch. Having been in the Army aviation for 6 years and had the opportunity to blow over 3 porta potties myself, only with a Bell 206, I was fairly happy with this. I think one of the key elements we look at in downwash and outwash as quantifying is the fact that the FAA and Engineering Brief 105 Alpha drew a line in the sand for the first time ever and quantified what the caution area is, basing that on 34.5 miles per hour. Now, the problem is I don't have any tools to actually ascertain what each aircraft in the inventory create during normal operations into and out of a heliport, let alone eVTOLs coming into and out of vertiports. But we now have a number. In 2010, this is my daughter. She'll love the fact that I added this slide. I was with the National EMS Pilots Association. This became an issue for us in the EMS world. And we looked at it and found out that one of the problems we ran into was EMS helicopters kept getting bigger and heavier. And what used to be a small issue started to become bigger and bigger issue. So we actually did this sign campaign. It's based on OSHA and ANSI standards. They have the orange, the warning, all based on what that definition is between caution and danger. So this all meets OSHA ANSI criteria. Hundreds and hundreds of hospitals throughout the United States now have these signs placed. And I remember when we first came out with the sign, it says stay back 200 feet. I got so much pushback because of that 200 feet. When in fact, we actually did some testing and said, yeah, that's about where we want people back from because of the outwash that we're seeing and the injuries that we experienced and the damages to different things. The challenge we run into is all the models that we have developed are on a stabilized hover or stabilized out of ground effect hover. It's rare that you see a helicopter at a heliport at a stabilized out of ground effect hover. A lot of times you'll see them on approach coming in or on departure. And the departure, and a lot of times in the United States or in the different parts of the world, can be 2 different ways. Normal departures come up vertically above the hazards, take off. So altitude, then airspeed. So they're coming up to a higher elevation, which is creating that downwash and outwash. Or if you look at what ICAO preaches as far as the backup takeoff, you see the aircraft backing up. So you're getting the downwash no longer on the heliport. Now it's moving off the heliport. Same with the approach and departure paths. That is what I need. I need something that calculates that a downwash as it's coming down from the aircraft after it transitions from effective transitional lift below and above. Right now I have a model that's right over the top of the heliport. I need something that I can calculate the flight path. One of the missing ingredients we have in the helicopter world is we don't have a good parameter I can point to that defines what a stabilized approach is for a helicopter. In the airplane world, there's a lot of material that says this is a stabilized approach. A really good friend of mine from the FAA and we brought this topic up about a year ago. It was amazing how much pushback we got from the helicopter industry when we broached the subject of, hey, we should define what a stabilized approach is. No one wanted to, which I found really interesting. What I have, so based on normal mathematics and physics formulas, created a spreadsheet that we can pick and choose different aircraft for a stabilized approach. And I can calculate what the average and the peak of the downwash might be at a stabilized hovers. Now, the thing is, I can't add the formula that says, okay, the pilot is on approach, he's decelerating, he's adding power, or she's adding power. They're arresting the descent rate, they're adding more power. Well, that's not a stabilized hover. That downwash vector and quantity is going to be much higher than a stabilized approach or stabilized hover, whether it's in ground effect or out of ground effect. I don't have the formula to actually figure that out. What I want is what we see in today's research when it comes to noise. We have contour lines that show me where the noise contour is for decibel readings around and how those propagate out and decrease. What I want is the exact same thing for downwash. This is 34.5 mile an hour ring. There's anything inside of that is my caution area. We know it's not perfectly circular at all, especially on that approach and departure path. That's what I want. Now, how do we apply that? I look at the risk analysis piece when we look at downwash and outwash. This is straight out of ICAO's safety management system. Frequent and occasional, likely to occur many times, has occurred frequently, yes. Occasional, likely to occur sometimes, has occurred infrequently. Anything we talk about downwash and outwash is going to be a 5 or a 4. Then we look at the severity side. If you look at 5 and 4, A, B, and C, basically intolerable region, but we allow it to go on constantly. So from a risk analysis standpoint, having data to plug into my safety management system based on the locations of my landing areas and the aircraft that are operating there would be huge on the safety side of the house. Now, our good friends at the FAA, I've had this conversation, Mike had pointed to it. We're talking about the fact that we have no good data. There is no reporting system on how to report or who to report a downwash or outwash incident to, whether it's injury or damage. Now, as a consultant that works in this space, I will tell you I've been hired several times over the last 30 years to represent individuals in lawsuits. Most of those have been settled out of court, so they're not discoverable information by the people in the public. And the FAA nor the NTSB has ever received a report from any of them. So ASIAS may be a good conduit for us to actually affect a reporting system, just like we do for bird strikes today, laser strikes, or drone incursions. Gathering good solid data is going to be huge to be able to actually figure out what the problem is. Again, lots of variables. We have an opportunity, I think, in talking with Richard Brown and Mike Price several times now, and we had the Downwash online discussion a couple of weeks ago. If you haven't seen that, it is online on YouTube. Please go look at it. I see a lot of opportunities for improvements in this space for us as traditional helicopter operators, but also in the future as eVTOL operators. This is just fun to watch. How to lose your first flying job. Actually, I've seen that happen. So that said, I'm going to go ahead and close out and give the next individual the opportunity to present, and then we'll have time for questions at the end of all the presentations.
Rex has been a great friend for VFS for the last 5 or 6 years as a advisor for infrastructure. And now I'm going to bring up the slides, I hope, from Dr. Mike Price. And I've actually known Mike for like 25 years in previous lives, both of us.
Thank you, Mike. Thank you, everybody, for coming today. I wasn't brave enough to risk a video in a presentation, so I'm glad Rex has worked. I'm just going to stick to words. As Mike mentioned, I've known him for 25 years. I used to come to conferences to present on the history of vertical takeoff aircraft. That's my background. I'm not an engineer. But I will give you some advice to start with, and it is simple, really. It is always meet your heroes. The guy on the left here is mine, Ralph Hooper. He's the reason I now work in civil aviation, because he designed the Harrier jump jet. He helped me with my PhD, and he also said near the end of his life, go work in civil aviation. So here I am. Mike Hirschberg knew him, met him a few years ago at an awards ceremony. But here he is when he came to visit Langley in the late 1950s, when in the UK, wind tunnel tests were showing that what became the Harrier, at the time called the Hawker P1127, wouldn't work. It wasn't stable, couldn't fly a transition. Ralph didn't want to give up. He talked to some guys at NASA who, when they visited England, a guy called John Stack, famous aerodynamicist, who said, come to Langley, we'll work it out for you. He arrived at Langley. They hadn't told the security at the gate he was coming, but he got on site anyway. And within a few months, Marion McKinney, one of the great, another famous aerodynamicist, had come up with an experimental program that actually showed the Harrier could be transitioned. And on that basis, the program went ahead. The key thing is we don't often understand what goes on the vertical takeoff, underneath vertical takeoff aircraft, helicopters, eVTOLs, jets. It's a really tricky area. And the reason that Ralph is my hero is because he learned to live with that uncertainty and to make things work. And I think that's the situation we all face. It's only through joint working and discussion, I think, that we're going to actually tackle these problems. So I've not arrived with a lecture at all. I've got some questions because I came into this from a military area looking at jet aircraft, but instead I was looking at civil aircraft, helicopters, eVTOLs. I kind of just had a lot of questions. I've been working with Richard Brown, who you'll be hearing from later. Basically, I ask the dumb questions, he provides the smart answers. But here are some of my dumb questions that I think maybe could provoke that discussion, and hopefully we can have it around the table today. One of the things that's really striking, I think, is our ability to understand safety. We've done some work recently that Rex mentioned, the UK Civil Aviation Authority with Richard Brown, where we went to measure some downwash and outwash. And because we didn't have very much money, we used handheld sensors, which meant we had to stand in the outwash field, and we felt it. And what you feel is it's not a steady wind. It buffets you and knocks you around. It actually has an effect on your mind. A cognitive effect. We were discussing this morning in a meeting with the FAA. There's a publication we've got called CAP 3075, which is online for anybody. There's a couple of references to it later. But at the heart of that, the thinking I've had is actually what we saw is if people weren't ready for what they would feel, the effects were worse than if they were prepared, if they'd been briefed, if they'd had a mental model that they could actually rely on to stabilize themselves. It worked for me, it worked for some colleagues. And I think one of the things we've got at the moment is perhaps some of the modeling that's going on is focused very much on the innate ability, okay? You have the Paxman model, if people have heard of that, which is a pretty burly US Marine in an outwash field who's trained, who's prepared, who's done, flashbang training to get used to being surprised and shocked by things and all sorts of stuff. But how prepared is the average member of the public? In the UK a few years ago, an elderly woman killed in a hospital car park when a helicopter came in and the downwash toppled her over. She sustained a head injury and passed away. And that's behind a lot of the work we're doing, is an understanding of how do you make people who are uninvolved third parties prepared for the effects of outwash and downwash. So one of...
Can you just ask if they can see your slide? Oh, there it is. Okay.
They can see the slides, I think. Okay, hopefully. Well, they can hear me. That's enough. I talk too much anyway. But I think one of the things we need to really understand is what's the end point you want to get to. And for the UK CAA, it's very much that third-party safety is the thing that no regulator can turn their back on. So a lot of the focus and discussion is on what the innovators are doing, and we're an enabling regulator. We want to enable those innovators, and it's by bringing everybody to that final endpoint and understanding where does safety really lie and how do we prepare for it, that I think it could be really useful to have a discussion. Mike Hirschberg's talked about in the past a thing called people call it the wheel of misfortune for vertical takeoff aircraft, where lots of the programs fail. And for eVTOL, is there a wheel of fortune? Is it the case that now we have the technology that can make these aircraft work? We did some modeling with Richard Brown, a publication called, not very snappy names, I know, CAP 2576. Again, that's available free online. But one of the products that came out of that was, okay, what markings do you have on the ground? Do you have a kind of a classic T-loft FATO helicopter marking? Or if you've got eVTOLs producing outwash spikes, do you have different shapes? My children, if you go to their school sports halls, what you find is they have painted lines for all the different sports they may play in different colours. Is that something we want to have? Do we want a really confusing area to land in? Do we have something that's dynamically generated? Virtual reality, is that how you do it? There's all sorts of possibilities. But how do we future-proof whatever decisions we make now by understanding what DWOW, as we're calling it, may actually produce in the future, I think is a really important area. We don't want to box ourselves in and limit innovators by coming up with something that works for the Mark 1 version of an aircraft, but not the Mark 5 that comes along in a number of years' time. Operations, I work in flight operations at the CAA, not the innovation team. And we're looking at this very much from that perspective of, okay, let's imagine these things in daily service. How do we make sure that happens in a safe way? How do you get to the 10 to the -9 or 10 to the -12, whatever number it is that you come up with that you want your sector to aspire and achieve? Are there differences? eVTOLs, I was just having a discussion with Rex before. I didn't know anything about helicopters until 3 years ago, really. And what I found is that helicopters are flown by pilots. That's a really obvious statement, but there's not a lot of software involved. You know, there's a lot of hand and eye coordination makes them work. eVTOLs, it's all going through the software. What effect does that have? One of the things we've learned is how to, from some of the recent work, is actually if you do what's called a Bedford rating, you look at the piloting capacity limitations. Is it actually safer to have pilots that aren't saturated all the time? Or is it actually, perhaps it may be the case that that lack of saturation means that when they have an emergency, they don't know how to deal with it. It's a whole range of issues that come up there. And Outwash can provoke those emergencies, even if it is just a tarpaulin suddenly taking out your rotors. One of the things we're working on at the moment is a large language model called VERT AI, which is taking test data from NASA reports and UK Ministry of Defence reports going back 50, 60 years and trying to see if we can actually throw up scenarios using that and test it against models so that we can effectively have a digital discussion alongside the spoken one among people. But it would be really good to end up with a usable database that can be shared openly, that we know is based on validated data, and actually models also are validated against that data. But if you ask me a simple question, which is, what's the one thing we can do? And this is one of my really sort of maybe a dumb idea coming out of my dumb questions is, I think perhaps we need to rename Downwash and Outwash. Most people I speak to who aren't in aviation, they say, what do you do? And I say this, and they're kind of like, what's that? What are you talking about? In the airliner area, jet blast kind of sounds dangerous. If we want people to be cautious around helicopters and eVTOLs and to watch out for outwash, I mean, outwash sounds like it's something to do with laundry for a lot of people. I think we should come up with a different name. And again, it's one of the things to discuss today. Here are some suggestions. These are just kind of like, popped out of my head almost randomly. Rotor blast, but is that just a one-off event? Actually, outwash feels like waves hitting you. Maybe vortex waves because it's produced by vortices. Prop gusts. You know, eVTOLs don't usually have rotors; they have propellers. I know this is a subject Mike has written about. But really, the main thing is, I think the objective of all this is to let people who are around these aircraft or operating these aircraft have some sort of mental model that allows them to deal with the dangers that are presented. So actually those dangers never appear. And that's me done. Thank you, Mike.
Mickey Raditich is from NASA, and he's going to give us a talk here.
All right. Thanks everyone for being here. And thanks, Mike, for putting this all together. You've already heard some, and you're going to hear more about modeling efforts, but I'm here to talk about one of the things NASA's doing right now in terms of getting more validation data for these tools to, again, validate these tools for multi-rotor aircraft. And you heard, particularly in the videos from Rex, about why we care about this. And so it's an important problem to understand and a hard problem to model. But on our side, what we want to do is to create high spatial resolution outwash velocity measurements for single and multi-rotor configurations for the purpose of tool validation. So the approach we're taking to this now is kind of a test stand and instrumentation cart based approach. So kind of getting very extreme configurability and variability in the rotor configuration. So being able to space them longitudinally and laterally and vertically separate from each other to model kind of any different configuration. And then having our instrumentation really able to move and probe anywhere in the radial or azimuthal field of the rotor. We're also looking into some optical methods that I'll talk about in a second, and running some of our own simulations as well. So our current testing plan, very, very soon in this summer, 2025, and really the week, basically as soon as I get back from here, we'll start testing our single rotor model. And we'll be moving on to a dual rotor, release that data and then the plan is to move into a 4-rotor configuration. So real quick, just on how we are kind of developing our points of interest here. We're looking at the NASA's RVLT reference vehicles that are kind of a family of vehicles that represent different configurations representative of urban air mobility. And so taking the different hub-to-hub distance and Z separation, vertical separation between the rotors, you can kind of see that a lot of things fall into kind of this bounding box of 2 to 3 radii rotor separation and 0 to 0.4, 0.5 radii vertical separation. So that's kind of where we're looking here to start. Now the test stands that we're using here are pretty simple. 5-foot diameter, being able to measure thrust and moment with collective and cyclic control. The big thing about them, though, is that they're height adjustable from 2 feet to 10 feet off the ground. So we can get down to 0.4 diameters off the ground, all the way up to 10 feet. So we can, change them individually. So you can look at different rotor heights configuration on the same vehicle, as well as that, vehicle, different distances off the ground and how your outwash is changing there. So this test stand exists, and, checkouts on operation, track and balance, data system testing, and making sure we don't shake apart due to ground effect, or ground resonance, sorry. And we're moving out to our test facility that I'll show in a second. So then the other big part of this is the instrumentation. So we have a mobile instrumentation cart, and it has a hot film rake that again can be moved into any point radially or azimuthally around this rotor system. So a big part of that is it's a fully independent system, so it doesn't depend on this specific rotor setup to operate. You could take it and put it next to any other hover test stand or full flying hovering vehicles. It is completely independent, so it is something that we'd like to use for a variety of different things in the future. And a little bit about what we're doing and why we're doing in terms of instrumentation is we're using a rake of hot films. And so the motivation there is that we can get really fine spatial resolution. So we can get down to a 1/2 inch off the ground and space those hot films about 3/4 of an inch apart to get kind of a dense field of our measurements. And it can also take very high rate data. So, we talk about outwash being chaotic and, very time dependent. And so we're not just looking at averages, we're looking at, the frequencies that are coming off of that and that high speed data. So sampling at 10 kilohertz, for example, on these hot films. We also have a sonic anemometer on here. And again, for reference, that's, about 5 inches diameter on the sphere, and that's a fairly small sonic anemometer, so you couldn't get that kind of spatial resolution. Also, the sampling rates are typically a lot slower at around 10 hertz. That chart there on the bottom left is kind of highlights why we are motivated to do that. So if you look at normalized velocities and heights off the ground, you can see that sharp knee bend where that peak velocity is. It can be a pretty small range, and so we want to really capture that distribution there with our hot films. So just so that it's real, this is a quick demo we had lying around of this cart operating. So you can actuate the rake vertically and also set the spacing of each hot film relative to each other, drive the cart around, and set the hot films back down where they need to be. So we'll be taking many data points around our rotor systems. The next thing I want to talk about is a optical method that we have kind of in development with our optical folks over at Ames. And that is helium seeded background oriented Schlieren velocimetry. And so the kind of general idea here, without getting too far into the weeds, is you can inject helium into the flow field, and with Schlieren imaging, you can see that the difference in refractive index that's caused by the different density of your gases. And so you can see those structures kind of moving through the flow field, and that's just fan forced flow. And then you can process that and take out velocity vectors to kind of get a velocity map of an area. So rather than point measurements, you can get, maybe a 2 foot by 2 foot window of what those velocities are doing. And our setup for that, to kind of get a good understanding here, is we have that helium seed rake to inject the helium into the flow. And then that measurement region, there's no box there. It's just to show that that's where we're looking at. And then with a camera with an LED and retroreflective background with a kind of randomized speckle pattern on it, you can look at, again, capture that difference in refractive index and then correlate that with the background and get your velocities. So again, this is a method that is in development from researchers at Ames and our partners at the DLR in Germany. And so they're developing this new method, and so we are hoping to see what kind of good results we can get out of it. We're also doing our own simulations. So primarily looking at CFD and conference analysis. So we're using overflow in fully blade resolved, as well as kind of a new feature in overflow, an actuator line model that models the rotor as an actuated line and then calculates the rest of the flow field as it normally would. And that is just to save in computation costs. So we're looking at the effectiveness of that. And then of course, comprehensive analysis, the even more computationally efficient and fast methods there. So of course, we'll be comparing our measurements, particularly in the single and dual rotor setup, to historic test data. And we'll be releasing all of our data into the community for everybody here to validate your tools. Now, I just thought I'd show this up here. Again, this is what we're talking about with those jets that form kind of in the symmetry plane between these rotors. So you get much higher velocities where the outwash here is interacting. Now, just real quick on where we're testing, I said everything's moving on to our test facility. This is the Outdoor Aerodynamic Research Facility at NASA Ames. So it's a big outdoor area because we're trying to avoid, of course, recirculation effects from walls and ceilings. But of course, being outside comes with being outside, and you have to make sure you're monitoring your wind conditions. And it's not just a parking lot, right? It is has the infrastructure we need to run the test that we need to do. So it's a place that has a rich history of rotor testing, and we are going to continue that. So as far as the workshop, I know we don't have questions right now, but in the discussion and talking to me afterwards, we are looking for what the modeling community wants in terms of data and what you want to see from us for us to kind of help scope our future tests.
So we're gonna, like, these types of detailed questions, we'll say either for this, after the presenters or offline.
Yes,
But
yes.
I did have.
Sure.
Whereas most multi configurations, more than 2 are used for colors. So are you looking at that as well?
Not in the current plans, but again, we're generating downwash and outwash, and it should be representative.
All right, so now we're going to switch to, I'll say our modeling and simulation companies.
Thanks, Mike, for having me. I expected a small meeting, so I'm kind of a little bit overwhelmed. You will see it also in my hot stitched presentation. First of all, Mike, I was thinking the entire time, I tried to come up with a nice word for downward outwash in my native language, German, but I couldn't come up with anything less than 30 characters. So maybe English is a better one. So good luck with that. I will be not any help there. But I followed your lead actually with my presentation, and also will actually have more questions and answers in my presentation as well. I will, for the sake of quickness, go through this. We didn't get any guidance of what to show, so I did my best guess. I remembered that I'm actually a mechanic before I became an engineer. So I tried to look at everything a little bit from the practical side. Why are we doing stuff? That kind of thing. So first I would like to say we are ART, we're doing Flight Lab and RCAS. I wanted to show from the toolmaker perspective, how do we experience downward outwash, the discussion? And I must quite frankly admit that Dr. Brown surprised me in Switzerland 2 years ago when he had the presentation. I thought downward outwash is something we have done for helicopters. So for eVTOLs, it's a go-do thing. We do the same thing we have done before. And he sensitized me to the fact that maybe we have to take a closer look. So here we are doing exactly that. Thank you for putting that together. And I think the reason why we're talking about, especially with AAM, is we have now the, on top of the 2 rotors that we are used to, we have now multiple rotors that are close together, producing thrust. Then we have adjacent ground surface, but we also have other structures around. And I think Rex talked about that a little bit. So we have downward outwash, but there's also more going on there as well. So that's why I, as a tool maker, would always try to understand downward outwash for what? What are we doing? Are we trying to design an aircraft that has very little downward outwash? Are we trying to maximize distance between lift rotors to maybe reduce jet streams? What is the tool that we are after? Are we looking into airport design? What is the interaction between a structure that's in very close proximity to aircraft is standing there with its own turbulent airwake and interacting with your downward outwash from your aircraft? Or are we after regulatory requirements? And I think that's what I'm hearing here is like, we want to make sure that we don't push somebody over that is walking by. We all remember 12 years ago or so, brownout was a big topic. So that's kind of related. That came to my mind right away as well. And I think Rex had some cool videos on this one. I wish I had more videos in my presentation as well for the same reason. And then traffic management. So we also have aircraft close to each other as well. So just clinical downward outwash, what is an aircraft in hover doing? And we can just see on a nice flat surface how it propagates. It's probably not what's going to happen in the real world. And that, of course, as a toolmaker gets you to the point is downward outwash prediction, how accurate do you need it? And how far away do you need this as well? And that goes back to the application we talked about. And then you will find, of course, very quickly that ambient conditions do matter, right? There was a measurement of ambient wind. It's probably not good enough because you have probably a large area. There's a lot of different wind going on in different corners of here. And we saw that in NASA Ames with the structures around it. There's a lot of stuff going on from the ambient that you have to catch as well in order to make sure that your predictions are correct. So just unleashing CFD might not be the one thing that we need to do here. Just as a background, I didn't know, again, I thought we were only like 10 people here in the room. If you don't know us, our company has about 40 years experience in modeling and simulation. And as I mentioned, we have done it for helicopters before, and now seeing the new configurations coming around and looking in this again. And one of the other aspects that our tools are used is to set up measurement systems again. I'm old enough to remember that we used to measure first before we unleash CFD. Now we do it the other way around. We measure to make sure that CFD was correct. And I feel a little bit of the art of measurement is lost. There are people that I could go to that would tell me where to put my sensor, which sensor would work, how to avoid obstructions of sensors. Just because you put it on a boom doesn't mean that you don't back pressure your sensor because of all the structure that's behind it. What is the secret sauce there? So I found out when I supported some of our customers on setting up a test campaign that we can use our tools to set up measurement systems, but it feels a little bit like reinventing the wheel. So to our community here is, I would also like to have some good guidelines of how do we measure this consistently throughout for different aircraft configurations as well. And what I found out is that, of course, when I do a viscous vortex particle method, I can put virtual sensors wherever I want in a domain. But then in the real world, you can only afford 5 sensors. Where do you place them? Do you have a horizontal grid? Do you have a vertical rake? Do you have both? Can you afford both? What is the sampling rate? And all this nitty gritty that you have to then do with the time synchronization with your ambient data is really tricky. So a lot of guidance, and I think NASA is exactly on this path. I was really excited to hear that. And of course, my presentation is different because I don't start with our tool. We are using the same tools that we're using for helicopters to do AAM as well. So we're using the viscous vortex particle method to do a lot of the work that we're doing for downward outwash. That's probably not a surprise to anybody. And I will skip those background slides here a little bit. We have done a lot of this work on helicopters before. Everybody has probably studied that in this group. This was one of the work I was actually involved in, inspired by Dr. Brown when he talked about these blast zone. I actually like this blast zone. It sounds dangerous, and it is dangerous. I stood under a helicopter, and it really changes your mind. And you see these blast zones coming out. So we have tools that predict those zones consistently. So now it's a matter of how far away do we have to predict it, and how accurate do we have to be there? Or can we use these tools that we have right now and change the design? Is there something in the design space that we can actually do closer to the aircraft as well? And then from the practical point of view, I already mentioned it. I'm very much have done wind tunnel testing in my life, flight testing, all this kind of stuff. Always comes back to me, tolerance, fault stack up in your instrumentation system. How is the instrumentation system calibrated? And then time synchronization. And then how do you get these, the weather station? It stands somewhere like very far away from you, doesn't know anything about the events that you trigger. And so how do you put it all back together to a data acquisition system? Sounds all boring. I apologize if you're bored to tears, but that is actually where that really happens, right? If you want to have really quality data, you have to have a thorough measurement system. Otherwise, what do you compare your simulation against, and how do you trust it? And then the other thing is, what I found out is we don't have ever enough money to measure stuff. So now you have to be smart about how you do your testing. And again, I could go usually to older people that have done it before and ask them how to do testing. But here we're talking about these, how do you change the azimuth angle of your aircraft to really make sure that the blast zone goes towards to your sensors. And it was mentioned before as well, maybe clean hover is not good enough. Maybe we actually have to fly into the measurement zone and actually depart from a measurement zone to get a little bit better of an idea of what's going on. And then, as I mentioned, environmental factors, that's actually where I came from. And I started with urban air mobility. I was really curious of how it feels like to fly in the downtown area with a really small aircraft through all the turbulent airway and land on the top of a roof. I stood on the top of a roof. I know it doesn't feel good. I can't only imagine how it feels to land there. So that's the next thing that I'm after actually there. You know our tools. I don't want to bore you with that. So with viscous vortex particle method in particular, we have used it for aircraft design, aircraft operations, and in special operations, where we thought we also address a far field. Far field for us was like 5, 9, maybe rotor radii away from the aircraft. What we are now talking about is, and we need a better word for that, is far field, right? We are now talking about 150 meters, maybe even away from the aircraft. I don't think any of our design tools have been there before. We have other speakers that can probably hopefully have the secret sauce for that. But so how do we use these tools, or maybe how can we combine these tools? Really interesting, because we want to go really far away to, it seems to be, get a really accurate number to make sure that the people that are in our airfield are safe. So far field is really something that's important. And then we will definitely talk about hardware limitations, modeling and simulation, especially if you're a CFD person. You know that you talk in weeks, months, this kind of time frame. Probably we need some tools that are faster. They'll give us answers much faster for more maneuvers, more different ambient conditions, that sort of thing. So we really, as a community, might want to come together to think about what is good enough. What is the accuracy that's good enough? And just fast forwarding to my questions here, I think Mike and I, we got the same memo. I have also just questions. When I got asked to speak here today, I had only questions, and I thought I put them out here. We don't have to answer them right now, but again, what is the accuracy that's good enough, and where do we have to have this accuracy? And then we also talk about maybe we can see it from the other way. Instead of predicting it accurately, maybe we can put out a specification, can say 100 meters out there, I can only have that much wind and that much fluctuation. You prove to me that it is correct. That's how it used to be. But then again, how do we measure it consistently? And what predictive tool can we use to get us to this way? And then how can we use these predictive tools in practical terms? Practical terms means how can I support an OEM today to help him through his certification? Because that's really what we're after, right? We want to make sure that the aircraft operation is safe so these aircraft can go out. And I wrap up here probably pretty quickly. And I think I overplayed my wind tunnel a little bit, but I'm really curious about this guideline of measurements. So I understand CFD, I understand the ins and outs from viscous vortex particle method. I know that we can only release so many particles, and if you go far, far away, our particles get lazy and to just linger around. We have still to compute them. So there's challenges in the hardware there as well. So we have to understand what are the measurement systems that we can capture this correctly. And I would like to really embrace Rex with his vertiport design, because it seems like we have to work together. Vertiport design and downward outwash has to work together because we have a structure emitting its own wake, working in conjunction with our wake, with the ambient air. There's no clinical situation where you only have an aircraft in a field, perfectly flat ground, nothing else around, and you will be happy. This will never happen. And so I'm a little bit older, so I asked AI to help me. Everybody says nowadays AI is the solution, right? So I asked, hey, AI, how does it look like? And that's actually, at first I thought it was just silly and I would not show it here today. But this is really what's going on, right? You have a rooftop with all these structures on there, and you have aircraft next to each other taking off and landing. So this is not like a clean outwash. And then Dr. Brown, I put also the grandma with a kid out there, because you pointed out that it's not always a 6'5" guy who stands there and has to deal with the downward outwash. And I found it interesting that AI puts it right on the roof edge, right? So it might be dangerous out there. So yeah, and there's windsock in the middle. So thank you very much for your attention.
So I'm going to actually give a presentation at the booth, CDI booth. It's about a half an hour long. I'm going to try to go a little fast here because I have a feeling people in the room would like to talk a little bit as well as us. So I'm going to just assume everyone knows who CDI is. We've been working in this field for very long. We've got like 150 years of experience right in this room, and that's individually. We have close to 400. No, we've been working in this for a long time, both with the helicopter industry and in the eVTOL industry. In particular, in terms of downwash, outwash modeling, we have a long effort for the Army where we developed a brownout model. We've worked with the Navy as well. We've got a history of validating our software, our CHARM software, for being able to predict the peak strength, the frequency content, the outwash profile. And so in the bottom there, you're seeing an Army brownout flight simulation. And the interesting thing about what we do is we actually are running this in real time. So we're sacrificing a little bit on fidelity, but we don't have any issues with CPU, any issues with distance away from the aircraft, because our vortex filament model has been developed to allow us to go in real time. And this is actually before GPUs. Now with GPUs, we can even do better. You can sort of see in the bottom right-hand corner, that's the wake. That's a CH-53 model of stuff straight from the Rotorcraft handbook, and a couple of plots from a paper we gave in the 65th forum when we're doing the brownout, showing how well we can predict the outwash, all these pulses, all the peaks in real time, as well as if you go to higher fidelity outside of real time. So just keep that in mind with what you're watching here. I'm just going to do one quick shameless commercial plug. We now, in the latest version of CHARM, have coupled with Richard Brown's type of viscous vortex wake model. So we have a Vortran M2 model, which allows you to do this viscous vortex, same type of analysis that Richard's doing. As a matter of fact, Glenn Whitehouse, our CEO, was a PhD student of Richard's, and then they worked together on this originally. So we're really excited about having this capability. We haven't used it to look at downwash, outwash yet, but we certainly would like to. So I'm not going to go into this a lot, but here's some output from the Rotorcraft handbook on the right. That's a CH-53 aircraft hovering over the ground. The rotor height is about 37 feet above the ground, and the red arrow shows you this particular data point is one rotor radius out. And on the plot on the right, typical plots you'll see, that's the velocity on the x-axis, on the y-axis, the height above the ground. The mean values from the experiment are the black circles, and the peak values are the black filled circles. And the charm predictions are the unfilled circles and the filled circles. And you can see we're not modeling the whole fuselage. And when you get close to the aircraft and you don't model the fuselage, you might get the peaks pretty close. We're just aiming for like 5 to 10 knots peak. And you can see that we're getting the peak to within 5 knots actually in this case. But you don't get the whole profile unless you model the whole fuselage in this case. As you move out, and if you come by the booth, I'll do more, but let's go out to 2R. This is near the peak, and you start to get more of the shape, and you also can see that we can capture the peak to about 5 knots. So, as Jan was saying, what's accurate enough? This would give you the ability to, within 5 or 10 knots, run things. You can run things in real time. They're in flight simulation, so you can run a ground approach. You can see what happens when you have a ground vortex. And I agree with what everyone's saying, and I talked to Sam Ferguson, who did the Rotorcraft handbook before this event, and the key thing is that these are very variable conditions. You can't just run one test and think you've got it, you know what's going on. There's different ground covers, there's different wind, they're trying to maintain different attitudes. It's something where you need to do a lot of testing and sort of take a statistical average to figure out what's going on. And obviously designers have to find the worst case scenario. It's not just when you're hovering in no wind. What happens when a wind comes up? What's the worst case that a person coming out of that vertiport lobby is going to get hit with something? So I'm not going to do more of these, but here's at 3R, here's at 4R for the CH-53. And then here's the same wake model, no changes in the wake model for the V-22. Not a lot of data that you can show on the V-22, even though we have access to it, it's not public, but this is one in the Rotorcraft handbook. This data point is in that direction where the peak velocities are, and we can match it. And I'll show one more piece of data. Mike was saying NASA's doing these calculations. This is a CH-47, so it's a tandem helicopter, and they put the plots there on the left of the port side, the plots on the right of the starboard side, so you're right in that jet stream. The black is the experimental data. The red is CFD, that's overflow of that actuator line and that blade. I forget what the R stands for, but individual blades. And the blue is the charm, and you can see that the charm is doing just as well in this particular case as the CFD, and it's doing a very good job of matching the data. I'm going to say this on behalf of everybody, ART, Richard Brown, anyone with an analysis. If someone runs your analysis, or if you run our analysis and you get bad results, it's just like a car. Come back to us and say, why am I getting these bad results? And we will help you get good results. That's what NASA did here. There are bad results out there with charm. I'm not going to throw anyone under the bus. They even publish their input. There's really bad problems with their input files. And it happens. When you have a code that you license to people, they run it, they publish bad results, they go and come back to you and say, why is it bad when you could have fixed it in 1 minute? So if you get bad results, come back, give me a chance to fix it. Okay, so this is going to be very interesting to some people because, again, these are my thoughts. And we argue about this at CDI, so I'm welcome to have people argue with me. But this mechanism is primarily inviscid, which is good news. It's very easy to capture this. What you see down at the bottom there, those are 2D inviscid line vortices. And watch, as they come to the ground, you'll see how they bundle up. There's a bundling of vorticity. It has nothing to do with viscosity, nothing to do with turbulence. On the right, there's an EH-101. You can see the wake pulse, pulse, pulse. We all studied with Pat Curtis, and Pat Curtis told me this. The frequency of these is proportional to the downwash velocity divided by the height. No blade passage frequency, just the downwash velocity divided by the height. You can go to the Rotorcraft manual and you can see it. The downwash velocity is about 50 feet per second. The height, when it's about 50 feet, you see these 1 hertz pulses. Now, we can do a lot, and because the primary mechanism is inviscid, we can capture a lot, as you saw. But when vorticity hits a ground boundary layer, that's a viscous phenomenon. And there's secondary vortices that get made. There's all sorts of interactions. There you're going to need CFD. You're not going to get that with charm. You're not going to get it with any other method except a CFD, high resolution grid. It might be very expensive, but that's the only way you're really going to resolve the boundary layer. If someone tells you otherwise, I don't think they're telling you the truth. They're modeling the viscosity somehow. So the other thing I'm going to say is I don't think we understand a lot about the primary physics of AAM aircraft yet. And the reason I say that is many times in my career, I thought I understood something, and then you do experiments and you figure out you were wrong. So there's a lot going on. These jets are real. It's not going to just be the simple case of a single main rotor helicopter. There's going to be a lot of viscous interaction between the wakes. And so we need to test, and we need to test in a lot of different configurations, knowing that it's always going to be different when you do it the next time. So I think we need to test the primary configurations. Very excited that NASA's doing that. Multi-copters, vector thrust, lift plus cruise. We could do model tests with route scaling, but we have to do multiple tests, and we have to do a lot of multiple configurations. So my final thoughts, take advantage, and Jan said this exact same thing. Let's take advantage of the people who've done this stuff before. I have 3 names up there, people that I called. They're people that know how to do these tests. Talk to them, consult with them. Also, they're people who've operated in big downwash, outwash fields. Now, these are military people, but now we're going to have civilians. It's going to be tougher, but they know how to operate in these fields. They know how to run these tests. Let's talk to them. Thank you, Mike, for starting this discussion, because there's a lot to talk about, and I'll yield the floor.
This is like our modeling approach in my group, as some of you know, is the Letts-Boltzmann method. We have found it to be a very interesting method for quick turnaround, especially if it's GPU based, which we have done over the years. We've ported it on GPUs. We can do up to real time. Some of the things that I show are real time, others are not. But this is really only the work that me and my students have been doing over the years. Also some experimental results that I'll be showing. But there's a lot of other stuff also going on at Georgia Tech. There's Marilyn Smith sitting over there, for example, with other real-time methods, machine learning based surrogate model approaches. There are some number of talks, I believe, also later in the week by students. Also, Alex Mushigian, not sure if he's here. Yeah, Alex worked a lot on tilt rotor, ground effect, wall effects. Near the Conex, the dive program was a big thing, right? A lot of you are familiar with that. Ship deck landing. I think a ship deck landing, well, Dan showed one, I think. So that's one of these scenarios where you have rotors interacting with the ground, with wall structures. You have an interactive wake, or a wake interacting with you, in this case from a ship. But you can have, you can have a ground structure next to you, like the hospital that was shown, or else where you have the exact same phenomena, just with, with winds blowing over solid structures instead of a moving ship that is going into the wind. But it's similar but different. So that's what I'm gonna start with here. What we have simulated in this case was a ship deck landing scenario. You see some of these phenomena that we are really after in downwash and outwash modeling, the interactions with the solid structures, right? And external winds or wakes. And a ship deck landing is a prime example where all of these things are coming together. You see here a Q criterion visualized. Now, shortly you will see some vector visualizations. Those were produced by Shreyas Ashok. He's sitting over there, one of my students graduating now. So you see these recirculations here from the, if you see my cursor, recirculation from the hangar door. You get it onto some parts of your rotor disc, but not others. So a pitching moment will be induced that the pilot needs to react to. You have a ground effect. It's all moving. So you have basically a partial ground effect or dynamic ground effect, because you're changing your height to the ship deck in this case. So you want to model this accurately, yeah, maybe, but it depends on the use case. If this is for pilot training and you need real time, maybe you don't need all of the little vortex structures. You may be okay. That's what we do here. You're okay with the larger scale structures, the tip vortices, the vortex structures from the ship, and you're not modeling those at the expense. Well, at the payoff of fast turnaround simulations or up to real time. So in this case, we have published those in the Journal of the American Helicopter Society. I think it was in February, March or so, where we showed all of those things, partial ground effect, time varying, recirculation. We haven't put this in the simulator yet. That's going to happen later this year or next year with NAFAIR at Pax River. But we have done a validation. It was brought up before here in this group from, I think it was Jan, talks about experiments. Now you can model a lot, but how do you know that you're right? You need a subscale or a subscale experiment or a flight test or a wind tunnel test or a mix of all of those. In this case, we went to a subscale wind tunnel test. I'm not going to go into detail of that, but you can look at those results. Then multi-rotors, the next little topic that I want to talk about. They interact with each other. That's also a lattice Boltzmann simulation, not real time in this case. I'm going to show a little bit more about the numerics later, but here I want to point out this unsteadiness that also Richard Brown in his UK in his report was pointing out, this unsteadiness. It doesn't look like a mean flow. It's not this very nice uniform flow. Dan pointed out there are peaks. So if you're operating there as a ground personnel or so, you are, you can't lean constantly into the flow and you're safe. No, it's a constant back and forth. Myself, having boarded a V-22 4 times, I can tell you that it's a constant leaning into the flow, going back, leaning into the flow, going back, because you get these peaks, then you don't get them, you fall over, you fall back, you fall forward. So that's what you see here. If you abstract a little bit and be a little bit creative, you see all these worms. Sometimes you have a constructive interference, destructive interference. You've probably seen a number of papers. That's all real stuff. And you want to simulate that to large wake gauges, so large domain. And the lattice Boltzmann method is nice in the sense that it's very, very little dissipative. And a paper will come out very soon, looking at the students in the right corner over there, very soon that will show how little dissipative it is compared to like Navier-Stokes approaches, for example. So I'm not saying it's better, the method is better in every aspect. It's good for certain things, and we found it to be good in quick turnaround, not getting all the little vortices, but the main parts that you're interested in for this problem, I would argue. And it's little dissipative, so you can actually track the vortices and the flow to very old wake gauges. We have simulated this setup here again for validation. We have published this in 2023 and 24. Journal papers are on the way. It's the setup is a little bit bigger than here. This was the first iteration of the rig. The second iteration is a little bit bigger. We're advancing the ground plane towards the, so we're bringing it up towards the rotors, not the other way around, because the load cells are very sensitive. So you don't want to really move them if you don't have to. And so we're doing the validation with our own experiments. And the simulations, back to them. I promised I will talk a little bit more about them without, I think we're behind time, so I try to speed up here. Like the domain in this case that you have seen was 46 by 46 by 14 rotor radii, so 14 high, 46 by 46, 24 million cells, small rotor, because we're actually simulating exactly what we did experimentally. This ran, because it's also about computational efficiency, this ran on a small cluster of 8 A100 GPUs by NVIDIA. You can see this on the right. It's rack mounted. So you can have this locally next to your simulator. If you have a simulator, you don't have to go to a high performance computing center. This computed 750 rotor revolutions, 10 seconds of real time were simulated, and it took 3 hours. Now, actually, the Lance-Boltzmann method is special in the sense that your time step is always linked to your grid resolution. And so if you're simulating smaller scale structures or smaller scale geometries, the time step will be very, very small. And so you run a lot of time steps, like this suggests, for like even a 10-second interval. And so a larger problem actually helps you in this case. So if we don't simulate a 0.2 meter rotor, but a 2 meter rotor, we're actually 10 times faster because we have 10 times larger geometry. And so then with a 2 meter rotor that you see on some current prototypes out there, you would do this in 2 minutes per second of real simulated time. And then again, and that's my last 2 slides. We want to validate those things. This is a pressure contour plot of differential pressure. You see sometimes in the middle, negative pressure coming up, fountain effect, because fountain effect was written about for the V22, for some other rotorcraft as well. So sometimes it's coming up whenever it's dark blue. But the point here is that it's all very unsteady. So it's not really doing it justice to talk of rotorcraft downwash or outwash simulations or experiments if you're only looking at the mean. That's not what we're after. That's not what is dangerous. It's really the peaks and the unsteadiness. And showing the last slide is showing a particle image velocimetry result, also video, which is in this plane of this quad rotor. And this, Mike, is really my last slide with the contact information if you want to reach out. So this is a little bit check it video, but again, it brings across the unsteadiness. You have the recirculation. Yes, if there was a fuselage body in the middle, then this looks different. So we didn't look at this. But you can see the vortex structures wobbling right, left, up, down. So it's really an unsteady problem. And that is difficult to catch for many of the methods, especially the lower fidelity ones. And that's what I'm finishing with. Thank you.
Well, thanks for having me, Mike. It's always a pleasure. Coming last in the row, I guess, gives me a slightly privileged position. The one thing is that a lot of folk have already discussed a lot of the things I was going to discuss, but also perhaps I can take a slightly broader position and give a little bit of an overview of some of the issues that I feel are important. And what I want to do is I want to be slightly provocative. I've titled my presentation "Looking Under the Lamppost." We all know the joke. The guy who loses his keys and ends up looking under the lamppost because that's the only place he can actually see. Now, what my contention might be is essentially to ask the question, are we merely solving the problems that we can solve, or are we solving the problem that we should be solving? And this is a personal perspective. See if you agree with me or see if you don't. And I'll try and cover this in 10 minutes so that we can have a little bit of time for discussion afterwards. So now the thing that we really need to realize, and we've seen a lot of great work presented this afternoon, is that our models and simulations are merely a way of encapsulating and communicating our understanding of the physical world to other people. If you like, it's a conversation between theory and reality. And I certainly see it as not just another way of generating data. And that's one of the traps that we need to avoid. It's all too easy to calculate rather than to think. And we need to try to escape from that particular trap when we continue as a community to try to understand the issues that we face. Now, the rotorcraft community, and especially the safety community, relies very heavily on a very simple and appealing model for the outwash. And I'm very glad to see folk like Sam and Mark in the audience today, because this is their great work that they did, admittedly a while ago, but it's a very influential formalism that has permeated the safety culture and has permeated the understanding of operators, of pilots and so on, as to how the downwash spreads out across the ground. And it's seen as this inverted bell shape where the flow just spreads out uniformly across the ground. In the case where you've perhaps got multi-rotors, then we might have these dividing surfaces, what Mike earlier called stagnation planes, and that might make things a little bit more complicated. The problem is when we look at this view of reality, its theoretical basis is such that it's somewhat problematic when it comes to rotorcraft safety. Now, why that is so is that the model is formulated in terms of an average jet-like flow. And if we try and find, so we can find the mean in terms of these jet-like flows, and if we want to find the maxima, we essentially use that same formalism, but we stretch out the same formalism using the appropriate juxtaposition of constants to end up with a slightly different curve than before. And we need to try and figure out whether there's justification, in fact, for using that particular approach to quantify the safety of vehicles in practice. Now, this is true of all theoretical concepts. As long as our mindset is framed in terms of one conceptualization of the problem, that's how we'll frame our calculations. That's how we'll construct our measurement campaigns. That's what we will measure and compute. And in the end, that's how we will frame the safety problem. So we'd better be sure that we're right. So does our boundary layer type flow or our outwash jet-like flow translate properly into physiological effect, translate properly into how we set up the arrays on the ground to actually measure what that outwash flow looks like, and then eventually into specifications for the purposes of defining vertiports and the like, as the FAA have proposed to do with rather simplistic measures of what the effect of outwash on the surroundings might be. Okay. So let's have a look at some of the fundamental physics and try to inform ourselves as to what we're actually looking for when we're trying to cope with this particular problem. Now, we know that the wake has a lot more structure than in this simple bell-shaped outwash type diagram. And many of the folks who've talked before me have shown essentially this additional structure. And it comes from the tip vortices, of course. The thing to realize, of course, is that the structure consisting of tip vortices is inherently unstable. And it is this instability and the growth of this instability and the interaction of these vortices with the ground and how that instability grows in the presence of the ground that governs how the outwash field develops and eventually what the velocity perturbations or what the velocities are that influence people standing in that outwash. Now, here's the really interesting thing. If we look at this particular diagram here, what I've shown is this descent, if you like, in two different senses of the word, from a coherent form of the wake down through increasing disorder to turbulence in the far field of the system. And that's for a rotor in free flow. If I put the ground in the way, then a simplistic view of how the wake interacts with the ground is essentially to place the ground at some point within this descent through disorder into turbulence. So if I have a high hover height, then that ground interaction might be turbulent. But as I reduce the height, that ground interaction becomes more and more structured. And Dan talked about Pat Curtis's velocity versus divided through by height representation of the frequency of these structures that are formed out across the ground. And this is the reason why there is that particular relationship. You end up with this coagulation of vortices, the structure of which is determined by how high the rotor is actually above the ground. Now, the point, essentially the summary, is that depending on the extent to which this instability has progressed, the structure of outwash across the ground can be very different. Yet the instability process is inordinately difficult to model. I think in true honesty, we can say that no code out there properly captures the progression of these instabilities below the rotor system in perfect detail. The problem is that the characteristics of the numerical process interfere with the physics to give you some analog to what's actually going on. And as it turns out, some numerical methods just aren't suitable to conduct that particular type of analysis out to any significant lengths or distances below the rotor. So the problem is, if we ignore vortical instability, then the simulated flow is bland and uniform, and the velocities within that outwash are actually quite low compared to what we measure. On the other hand, if you account for those vortex instabilities, then if we look at the snapshot of the flow below, in that case, it's an S92, then you can see a lot more structure in the outwash field. And indeed, the velocities within that outwash field are significantly higher than you would measure in the mean. Now, it's those maximum velocities, depending on how long they persist for, that tend to pose the greatest danger to people standing in the outwash. And the problem is, of course, that this is the kind of velocity trace this is a simulated velocity trace over a period of about 80 seconds. And you can see that if I stick in the mean velocity or the average velocity in there, the average velocity bears very little relationship to the velocity that I ever see within the outwash field. It's a figment. It's a post-processing artifact, if you like, of the actual signal that we see. And similarly, the maximal velocities are a very dangerous characteristic of the outwash to actually try to encapsulate, because how do we actually know whether this is a persistent feature of the flow or whether it's a one-off, it's a black swan, and that's something that we really need to account for. So when we measure these velocities and translate them into our statistical variation, we need to be very careful of what we're doing. And I don't think the science has actually caught up with the reality there as far as the kinds of techniques that we actually need to implement. Now, if we stick a number of rotors together, multi-rotor vehicles, so I'm getting away from the idea of a single rotor system, then what we find is that the vortical structures don't actually obey a very simple dynamic. Here we have these dividing planes, if you like, between the flows generated by each of the rotors. Here I have a fairly simple quadrotor system. And here you can see there's a fairly simple division of the flows into their separate domains, this idea of these stagnation surfaces that Mike brought up. The interesting thing, though, is that in the presence of vortical instabilities, those stagnation planes do not survive. Symmetry breaking destroys them. There never is the static point within that flow. It keeps on meandering around. And actually what we find out is that as that breaking of symmetry progresses, we find that those broken areas of broken symmetry are actually where these jets form, where they originate and where they tend to spread out from. So when we end up with a flow that's rather more developed, then you can see that hidden in amongst all this mess and chaos are elements of order. There are jets going out to the side here, a jet going out to the front, a highly turbulent wake, in this case behind the vehicle, because the rear rotors are slightly higher than the forward, and a somewhat sheet-like structure in front. So that's the sort of thing we should be looking for, and we need to set up the experiments in the proper way. Now, let's have a look at what happens when we try to simulate these systems. How far out from the system do we actually need to simulate the wakes? And this is huge relevance to the different types of numerical techniques which might be appropriate. If I run this out to 30 rotor revolutions, you can see the symmetry breaking taking place there. And what I'm doing is I'm plotting vorticity just above the surface of the ground. But you can see the flow has hardly gone anywhere by the time that 30 rotor revolutions have taken place. That's far too short a simulation to pick up any particular detail from the flow. So the kinds of simulations we need to do are much longer. This is a simulation which runs up to something like 400 rotor revolutions. And you can see that the flow just keeps on going. There's very little dissipation, especially in these jet-like structures which tend to emerge between the rotors, and they can propagate out for tremendous distances away from the system. Okay, so we need to resolve the vortical structures within the flow. We need to resolve the instability mechanisms and represent those accurately, and we need to leave the flow alone, give it time to develop before we even start to sample it and to gain statistical information from that simulation. Now, what does this mean if we try to abstract our simulations through into the real world in terms of what we might do in terms of observations? Well, let's superimpose the velocity variations on top of a very simple grid, the kind of grid that the FAA was using in the initial series of tests on aircraft like the Joby S4. Now, you can see that the complexity of the flow field poses extreme constraints on the spatial density of the sensors that are required and the frequency bandwidth which we need to measure the data. That's one thing. That seems to be fairly obvious to me. In this case, you can see that this density of sensors doesn't actually resolve many of the details of the flow in with any particular accuracy. So what do? As Jan said, we perhaps only have 15 sensors available to us, so can we use those effectively? Well, the question is, do we know what effective actually is? How do we bulk out the data using the very few sensors that we have actually available to us? And I would suggest that the strategies for bulking out data need to be approached with extreme care. For example, this idea of setting the aircraft at a certain height and changing the azimuth of the aircraft and measuring again needs to be looked at in a lot of detail, given the time that it takes for the outwash to propagate, the overturning time, the replacement time of the flow in the outwash is measured in many seconds. It's not an instantaneous kind of thing. So we need to be careful to retain the statistical significance of our data when we use very few sensors and perhaps when we use techniques for bulking that out. And I've suggested earlier that the statistical basis for reporting the data may need to be reformulated in a proper investigation. Now, this gets to the crux of it. Okay, there's my granny picture that Jan was referring to. Essentially, that the way that we currently encapsulate the physiological and psychological responses is misleading if we adopt an overly simplistic representation of the outwash field. And this is where things reach a crux, because this is really what we're trying to do when we're trying to solve the safety problem. We're trying to figure out what the influence of the outwash happens to be on the people who are immersed in that outwash. And if we're taking a historical approach where we look at a simple overturning moment on a burly US Marine, then the basic question is, how apposite is that when we start to look at highly transitory flows, perhaps aligned along certain axes, and where we have people who are perhaps do not have the full faculties or the physical strength of the US Marines. As Mike Price was saying, perhaps the physiological and psychological responses need to be separated out into a preparedness and an adequacy of physical how adequate the person's physical tone is to respond. Okay, and the last thing, the real crux is that this is certainly not an academic issue. It's not something we can sit around the table and discuss nice numerical methods and sort of inch towards a solution. It's a real problem with practical consequences for the AAM industry. It influences the design, layout, and positioning of vertiports, effective operational procedures, doing approach, landing, and takeoff, as Rex was saying, and the ability of certain aircraft even to operate from specific sites unless properly designed to do so. So it's an issue of interest to designers, operators, and regulators alike. And so, in summary, we need to do what is necessary to solve the safety problem. We need to understand the physics before we try to model, and we need to know the physics before we go ahead and gather data. We need to know what we're looking for before we even step out into the field to gather random data. And good numerics can help us ask the right questions. And I think that's the real synergy here. Exactly as Dan was saying, we need to get together with the right people, get them in the room, get the numericists together with the experimentalists, thrash out the procedures, and go ahead and do this in a properly structured, interactive, and collegiate way. So modeling outwash correctly is one of the trickiest problems in rotorcraft aerodynamics. That's part of the course. That's something we know. What I contend is we may need to leave behind some of our cherished assumptions and methodologies to actually solve this thorny problem. And this indeed may involve venturing a little further out into the unknown than we might find comfortable. But certainly the dark out there is not a scarier place if you have the right companions, and I think we're heading in that direction. So I'll cut things short there. I'll stop, and we can hopefully have a little bit of time left for some discussion.
All right, thank you, Richard. Thank you, everyone. So let's start with just anybody that wanted to say anything that hasn't been able to say anything yet to this period.
Yeah, I have the answer to one question that was asked, and then I want to throw out a different perspective. Nikki, you asked what the computational people want from your test. I'll tell you, please don't just give us averages. Please save your time histories. We've got SSDs that will save terabytes of data. Because what we need to answer the question, are there bifurcations? What are the sensitivities to the unsteadiness in flow fields? What is good enough? To do that, we need all the unsteady data. So please save it out. Please do a tear before and after to get, as Jan was talking about, the ambient conditions and things, again, because things change during time. And again, the influence of the obstacles. So that was my short answer to your question.
Yes, thank you.
The other thing I want to throw out is that one thing that struck me with all of these discussions was that the helicopter was acting in a vacuum. In other words, I mean, there was air around it, but it wasn't real life. Because when we talk about what's happening here, and this is going to my research, is that we're going to be in AAM and in these other things. We're not going to be operating by itself. We're going to have all sorts of different unsteady flows coming in from the buildings, the obstacles, from ships. We've got the turbulence in the clear turbulence, things that are happening. And then they all interact together. I mean, the case of the elderly woman at the hospital in, was it Bristol or? Yes. So at Plymouth, I mean, is a very standard test case. When they designed the Hellcat, they designed it and it worked. But for that day, the wind, the atmospheric conditions, and the helicopter, the way the operating conditions coming in, cause a very unsafe condition in some part of the parking area. Okay, so I think we've got to do that, because here's the thing, I think probably we all got a bit of a pass there because it was a helicopter doing life-saving operations. We're not going to get that pass just standard cargo or air taxi. And it's a business where people are making profits. And, we saw what happened in 1960s, the Sikorsky helicopter building in New York City. How many decades before we started talking about doing this again? So I think we need to be careful with this. So I would like to challenge everyone to not just consider doing the standard problem. Yes, I think we have to do that, pressure based, but then I think we really need to understand the physics. And building on what Richard was saying, is we need to understand the physics of what's important and what's going to drive all of these things. And I don't think that it's going to be the helicopter and the ground effect alone. I think it's going to be the helicopter, the ground effect, and its surrounding areas, and we have to do all of that. Otherwise, we're staying under the lamppost. I like that, Richard. So I'll shut up now and get the thing passed around.
Yeah, okay. So Sam was next. Go ahead, Sam.
Okay, first of all, I want to thank everybody for getting together and discussing this today. And I just would like to ask, when the first meeting like this was happening and the first report was turned in September 1986, when we had a 512 kilobyte line input computer with a Fortran compiler, where were all you CFD guys? So could have used you then. But also want to apologize. I've heard the mean velocity come up in this meeting, and I've read it a lot in the recent reports. And just want to make sure that everybody understands that when all this got started a long time ago, the mean velocity was really a meaningless number. It was a way to get to the peak velocity, which was the hazard. And so anyone that thinks that in the early days that we were somehow thinking mean velocity was meaningful and we didn't fully understand the stochastic nature of rotor wash and everything, we were constrained by the product. And so therefore we had to make a lot of shortcuts to be able to get where we got to turn out something that met the needs of both the civil in the early FAA reports and some military work. And as a result of kind of some of the things I've heard today, I kind of back up what was just said too. I think that me particularly, because I haven't done a whole lot since 2014 with John and Mark Silva, no one knows what's been done and nobody knows what's being done and has it all in one brain kind of all together. And that right there is an internal product that the VHS should take extremely seriously, because I've seen some slides, and I don't want to pick on Dr. Brown, but he noted that, there wasn't a lot of civilian stuff. Unfortunately, there is. It just may not all be well known. There's a PAX boy, there's statistical body types, there's railway, high-speed railway from, I think it was London or Birmingham data that shows how people will be startled on the side tracks and what that effect can be. there's a tremendous amount of stuff out there. It's just, unfortunately, it's not really in the public view. And it's no one's fault. No one's done anything wrong. But until that gets out there, we're going to be solving some problems we don't need to be spending money solving. And Appendix C of what's Richard's reference 6 has some of that stuff that might have just gotten overlooked due to all the junk that was in there. So, and another thought I have is Rex presents an example of something I think we need to take extremely seriously. And it's just as much or more important than any of the analytical work. Rex presents the product that's needed by the people in the real world that are going to fund the research and are going to stick with trying to understand rotor wash. We would love to have turned a rotor wash product exactly like Rex wanted 30 years ago. It was not possible. The number of configurations of aircraft, the number of permutations, a height above the ground, speed of the approach, what's the wind direction from, that's all was way beyond the technology of the time, not only to calculate, but it was way beyond the technology to afford to take that data and get that data in a way then it could be turned into a meaningful requirement, which I noticed Jan brought up the point that was very important. And it's another internal product of EHS. And that's how we really need to understand how we use the sensors, what type we use, because there's a huge affordability and cost involved in this. Mark Silva probably could throw out a number that to do one of these major tests on a CH-47 was $1 million, $2 million for all I know. I know for one test I did that unfortunately it's proprietary because it had some approach and landing data in it that even with getting somebody else to pay for it, we had probably a group of 30 people full-time for 2 weeks to get that test done. So just the salary alone in there would have been a lot of money. So the whole issue of sensors and everything like that needs to be discussed. Lessons learned needs to be passed on. I might add that it's in reference 6 and other locations. Handheld mechanical sensors, they shouldn't even be used for rotor wash tests. They ought to be banned as only devices which maybe give people a round number feeling, but for taking any data that goes into any database used by any analytical tool. All that data should not be used and it should not be taken. And the focus on laser and optics is the way to go. We had an opportunity, which I don't know it's very public either, to take trailing wake vortices behind a couple of helicopters and 2 tilt rotors about 18 years ago when laser optics were really state of the art. And we were able to do on one of the afternoons a side test of measuring outwash profiles, which are in that reference 6 in the back of the report. And with no setup, no special software, no nothing, the laser optic acquired data was extremely promising compared to the data traditionally taken like the way Pax River takes. And that's certainly the way to go, particularly if you want to be doing mathematical modeling and stuff like that. So I think where I'm trying to come to an end here pretty quick is I think you need to step back and everybody needs to figure out what's the path forward and what are the products we want to produce. If we want to produce data to correlate programs, that's great. I'm all for it. If we want to produce data that eventually becomes data that's suggestions to agencies like EASA, FAA, that's a whole different path, which requires a whole different set of decisions and programmatic money authority to come about. And then if you want to get to the point where you're actually writing regulations, that's another whole issue to itself. And that brings up one other thought too. I just throw it out there because I want it on record. everyone involved, if you're not aware of such documents as NASA CR 2021, NASA Standards 7009A, AIAA R154 2021, and I don't have the EASA or the Department of Defense numbers. Everyone is now starting to put out guides for things like aircraft certification by analysis, standards for models and simulation. I would not expect or hope that this type of work would necessarily get hit with those standards in their, I'll say, most complete form, but it's quite possible that you could be in 5 or 10 years could be forced to produce that, or your data won't be considered valid enough to use for certification or anything like that. So as a group, I think VHS needs to keep in mind that the rules of the road are changing in the helicopter rotorcraft industry about what you can do with modeling and simulation. And it's changing really quickly. And all of those documents could end up becoming requirements. And that's a whole nother discussion also in itself.
Okay, great. Thank you so much, Sam.
Okay.
And I do want to point out that we do have, I don't know if you can see this, but we do have a number of documents on our Downwash, Outwash library. So send more documents that you think are important for that. We do have the downloadable, both the volume 1 and 2 of your rotor wash analysis handbook. So we're at the kind of the official stop time that we had planned, and I just want to, I don't know if you can see this or not for you guys online, but just the original slides that I was, let's see if it goes here. Yeah, the original slides that I was presenting here. So we're focused here on the workshop, mainly because the FAA is taking data on commercial helicopters with the view towards advanced air mobility. There is a lot of stuff, optical air data systems, others that are looking at advanced, ways to measure downwash and outwash. So we can talk about, I'll say these third and fourth bullets here, but the real question is, do we want to, right? Okay, we hear a lot of people talk now for 2 hours. Do we, the people in this room, the people that are online, do we want to do something about it? What is, this is all nice just to listen to this, and we have a recording of it too, so you guys can refer to it, but hey, what do you guys want to do with this? I started off with talking about some of the AIAA Hover Prediction Workshop, HART, STAR. Should we, you guys, the technical community, do we want to continue having discussions on this? Should we just form a discussion group? Should we have grand visions or just move on?
Yeah, so there's been a lot of talking about work. So we've done a lot of rotor wash measurements, I guess, over the years. And so what we notice is that a lot of the modeling does actually work pretty well. So rotor washes scale between different helicopters as you would expect them to scale. They have some holes, as you noted, but the peak scales to the mean as you would expect it. You have a rotor that's producing double the mean, but peak doubles as well. So I guess the question is a bit, all right, there's those error bars, right, which are killing. So if you do rotor testing, first thing you notice is people who do CFD and people who fly helicopters, hover is not the same thing, right? So for a helicopter pilot, hover is there's a 25 knot wind and your aircraft is stable. So that's hover for a helicopter. For a CFD guy, your rotor normal is vertically upwards, which is not a situation that ever happens in real life. So let's say that there's a few of those things, which I think is trying to define what's the question that we're trying to answer, rather than sort of say everything's not working well. There's a consistent advance, in what we're doing. I think there's been a lot of steps to getting better. Certainly don't think everything in the past is not helping us. There's really a lot of good stuff out there, which is very predictive also for these new configurations.
Anybody else in the room or online? Okay, Jan?
Something that Dan said really resonated with me when you asked where we want to go from here is I totally agree. We have tools that can predict a lot of the phenomena correctly, but what I feel from the industry is there should be somewhere where people can go and ask these questions on how do I do this, and not just doing a paper research and finding papers on good luck and doing it, but having a VFS group to go to, and they will maybe guide them to the right answer or the right people to set up the experiment or how to do best practices, or as Dan said, how to set up the initial conditions correctly on your simulation, that sort of thing. So if this workshop could be the graveyards of downward outwash, that would be probably appreciated in this way.
And I should mention again, like we had expected or hoped to have someone from the FAA speak about what they're doing currently, as well as, the Army's had a lot of research in this area. So we had hoped, we had planned to have speakers from those organizations as well. And as mentioned, they weren't able to get permission to speak about this important safety area. So if we, if this group was so motivated, it could be potentially a, interagency and, international discussion group, or, community of interest action group, or some other, potential path forward. Yes.
Hi.
Sorry, you need to speak in a mic.
Hi, Dave Eisen, WashDOT. Just wanted to piggyback on something that Rex said, that typically the downwash, outwash issue is not something that's covered in training. It should be. And so I think we have an opportunity here to not only use the data for designing safety zones, et cetera, for vertiports, but also for training requirements for powered lift aircraft that are going to be coming down the line. It's going to have to be part of the training program. The other thing that just hit me while everybody was talking is maybe one of the other things that we need to be looking at is how do we minimize, mitigate, destroy the outwash with the design features. I know there's Clem Brown, I think his name is, in Australia, who has a patented vertiport design, and it uses, a variety of different means to mitigate the downwash, outwash.
And you please tell us who you're representing.
Johnson Aeronautics. I would hate to see you adjourn without a path forward. I would point out that you do have within the VFS appropriate ways to define a path forward. And I would suggest that one of them would be that the subject falls within perhaps the joint domain of aerodynamics committee and test and evaluation committee, and their committee meetings. Well, aerodynamics might have been already done, but anyway, hopefully their committee meetings might address it. I would also point out that the next VFS opportunity that would fall within this subject would perhaps be the air mechanics meeting next January. I think you do need to, before you adjourn, to identify who might be tasked to take up the mantle to figure out the steps forward. Otherwise, there will be no follow-up.
Very well said. So many of you know I'm going to be departing VFS later this year, but want to continue to help support the organization and help VFS continue to do important things. And this is one of those things that I would be very happy to continue to support. Once I get the sign-in sheet, we'll send out emails and we can have, follow-up Zoom or Teams meetings. Dr. Johnson's comment about the next transformative vertical flight aeromechanics meeting is being held in January, end of January. And that will be in San Jose. Abstracts, I think the call for papers is out now and abstracts are ready August 4th. I think it's online. I think it's posted. So that would be, it would be great to have either a working group meeting and or lots of papers for this and hopefully sharing information. I think that is one of the things is there have been a lot of reports and a lot of, I'll say analog measurements over the years. And I don't know what the FAA, what their testing and measurements are going to be. Hopefully, as I mentioned, maybe dozens of helicopters and eVTOL aircraft. They felt that was going to be proprietary information that wasn't necessarily going to be able to be shared, but like if there was interest, we could try to have the FAA, NASA, Army, Navy, others talking to each other and maybe sharing experience and expertise, potentially have a government and industry and academic working group as well. All right, where's the sign? Okay, we got one more person to sign in. Okay. Yeah.
Yeah.
Oh, okay. All right. Well, you guys are gonna have to come over and sign in. So I plan to like I said, send out emails. I need some more volunteers to move this forward, or so I have Professor Smith, Marilyn Smith, but just this is your society. This is your technical community. Get involved all day, every day, and let's help move things forward.